Hello, I'm Alec, and today I'm going to tell you about some work that I did with Virginia on listing the six cycles in sparse graphs. So pattern detection and listing are two very fundamental problems in algorithmic graph theory. In any of these problems, we're going to have a pattern graph H, and we're going to have a host graph G. We think of H as being really small, constant sized, and G, and we're going to kind of let M and N denote the number of edges and vertices in G. And throughout the talk, when we're kind of making algorithms, we want to make the running times be fast in terms of M and N. So the question, the kind of two simple problems you could ask with this H and G are, does yes or no, is there a copy of H and G? And list all the copies of H and G. And in this talk, we're going to focus on even length cycles because these have some really nice combinatorial structure, which I'll tell you about that right now. So to understand why even cycles are really nice, it's useful to contrast them with odd length cycles. So odd length cycles, it turns out that the fastest algorithms for detecting them go through fast matrix multiplication. And this is kind of unavoidable. And so this means we're going to have some running time like NC omega, which is nice, but I guess it's yeah, it seems pretty tricky to improve, and there's not any like cool combinatorial things that you can do. It's this very complicated like matrix multiplication stuff. But in contrast, even cycles are very different. It's a very different story, at least for detection. User and Zwick in 1997, they gave a quadratic time algorithm for detecting any constant length even cycle. So why is there this big difference? Why are even cycles so much easier? It's because in order to avoid an even cycle, your graph has to be sparse. Whereas you can have a very dense graph that avoids odd cycles. To make this a bit more precise, we have this theorem by Bundy and Simonovitz. For instance, one case that we especially care about is if you have more than n to the 4/3 times 100 edges, then you must have a 6 cycle. Great. So that's kind of intuitively this type of extremal result is what makes possible to do better, like really interesting algorithms for detection and listing for even length cycles. So now I'm going to tell you specifically what we actually know about detecting even length cycles. So as I kind of just told you, there's this quadratic time algorithm from User and Zwick, and we think it's probably optimal in the dense regime, although we don't really have any super nice lower bounds based on other problems that people like to assume are hard, even for 4 cycles. But if we're in the sparse regime, we can do better. So for instance, with like 4 cycles is a very simple algorithm that can do m to the 4/3, and more recently, Dalgaard, Knudsen, and Stoffel gave an algorithm with this running time. And there's some reasons to think that this is optimal. Maybe the most nice one is just like if you could improve this exponent here, then you would also beat the quadratic time algorithm for the dense regime. So this seems like this is probably the right number. And just in summary, we have a pretty good understanding of even cycle detection. So that's the story for even cycle detection. But now I'm going to tell you about listing, where a lot less is known. So in listing, we're going to let t denote the number of cycles, and our goal is to list in time detection time plus t. Or I guess what I mean by our goal is I personally conjecture that this is probably possible to do, and obviously you can't do any better than this. But we don't know how to do this well in most cases. So what do people know? There's some kind of baseline result by Alon, Euster, and Zwick that does this well. It's not bad. But then kind of more recently, for small values of k, there's been some work that has gotten actually things that we think are the right thing. So for instance, Jin and Xu gave this algorithm for 4 cycles, and this feels like the right running time for 4 cycles. So specifically, like this is the optimal detection time. So to beat this, you would need to have a better detection algorithm. And then Renfei and Virginia gave this nice algorithm for listing C6s in the dense regime. But that's pretty much it. That's what we know so far. So kind of you could think larger values of K or even the sparse regime for C6s, we don't know how to do detection time plus T, and we definitely also don't have any kind of reason to believe that you can't do this. So that's what we looked into in our work. The next natural question, which is, can you list C6s in time m to the 1.5 plus T? For context, what was known before about this, like obviously we have this dense listing algorithm, and then you could use the Alun-Euster-Zwick one, which gives you like m to the 5/3 as the exponent. So this was our question. I guess we thought about a lot of questions. Maybe we hoped to understand this problem more generally, but what we were able to show is that we got some improvement over the previous best known 6-cycle listing algorithm. So in particular, we got the exponent down to 1.6. Yeah, I think in the rest of the talk, I'll tell you a bit more about just how we think about 6 cycles and what were some of the important ideas to both to get this result and ideas that I think could help getting better results and maybe even resolving the entire question of how fast you can list C2Ks. So yeah, so that's what I'll tell you about in the rest of the talk. Okay, so listing algorithms. The most natural thing you could try is probably the following thing, and it's not going to work, but if we modify it a little bit, it's going to be pretty good. So here's like a natural strategy. You could start by splitting the vertices into 6 parts via color coding. So just like randomly assign each vertex to one of the parts, and then only look for hexagons where you have 1 vertex per part. And like we'll repeat this a couple times to get all the hexagons. And then once you've split them up like this, maybe what you could do is just for every vertex in one of these parts, you could do like a little 3-step BFS or something, and just for every pair of vertices, you keep track of paths between them, and then you combine paths to get 6 cycles. So okay, so that's something that you could do, and like sure it works, but how fast is it is the question. And it turns out it's not quite as fast as we'd like. So specifically what goes wrong is there's some graphs where you have a large number of these 3 paths, but you don't have enough edges and or cycles to pay for it. So specifically, here's a graph which is very sparse, no 6 cycles, but it has a ton of 3 paths. So we can't afford to list 3 paths if we want that running time that we said we wanted. But it turns out that there's a slight modification, like a slight modification of the idea of a 3 path that was introduced by Dalgaard, Knudsen, and Stockwell, or DKS, in 2017 to solve the detection problem. And these capped walks that Dalgaard, Knudsen, and Stockwell used, they're really gonna also be key in our listing algorithms. So yeah, I'll tell you about them right now. So a capped walk, the idea is just basically think of it as the first vertex is higher degree than all the other vertices. That's the way to think about it. And now our new algorithm is, instead of just listing all of the k-paths or whatever, we're going to only list the capped k-walks. So the ones where the first vertex is the largest degree in the path. And we'll also maybe do some special casing for some very high degree vertices, which is going to be okay because we just don't expect there to be very many of those. So the way that you should think about what's happening here is within every cycle, like maybe a 6 cycle, you could say, has 6 vertices, and we're going to designate one of those to be responsible for listing the cycle. So like this one vertex is going to do its 3 set BFSs and then kind of collect those to make the hexagon. Whereas before we didn't really have anything distinguishing any of the vertices in the hexagon. So, okay, I mean, that's maybe an argument that this is still going to catch all of the 6 cycles. But now the thing that we should ask is, maybe we should just at least quickly run this against the bad case that I had showed you on the previous slide, where we had tons of 3 walks, but no edges or 6 cycles to pay for it. So here's that example, and if you look at it, you'll notice that it's looking pretty good. There's 2 high degree vertices, and let's say we just don't care about those. And then if you, once you like kind of forget about those guys, there's not any other capped walks, because the walk would have to start at one of these really low degree vertices and go through a high degree vertex, which is where we're banning that. So at least in this case, like we can afford to list capped walks out of like not ridiculously high degree vertices. So this idea kind of solves this one bad case, and it turns out that this actually just solves all your problems for detection. So specifically, DKS, we're able to show that if you have a graph that has more than some certain number of capped K walks, then it has to have a C2K. So what this means for detection algorithms is basically you can just kind of assume that you only have this many capped K walks, and then the algorithm that we said where you just list these capped K walks just works because there's not that many of them. By works, I mean is fast. So that's like the idea for how the detection algorithm works. And the basic idea for how we would want a listing algorithm to work is like, or so here's kind of what you would hope for maybe. So the DKS algorithm for detection is based on the observation that lots of K-walks, capped K-walks implies there's at least one C2K. So for listing, what would be nice is if there's lots of capped K-walks, then there are many C2Ks, right? Because like if our plan is just to list all the capped K-walks, then we need to know whenever we have a lot of capped K-walks, we have a bunch of C2Ks that can pay for the listing of the capped K-walks. So that's kind of ideally what we'd like. And to understand if we actually have that kind of a result, we need to maybe understand how this fact 3, how the proof of that works. So the proof of fact 3 is based on kind of a generalization of the classic like extremal number result for cycles. So the classic extremal result for, say, for 6 cycles just says if I have a graph and it has more than omega n to the 4/3 edges, then it has to have a 6 cycle. So that's this picture on the right. But there's a generalization of this to a case where you have kind of a bipartite graph with 2 parts of unequal size. We call this the unbalanced extremal number. And here, for instance, if your parts are these sizes, then it turns out you need a lot fewer edges to guarantee a 6 cycle. So maybe if your parts are size root n and n, then having n edges already guarantees a 6 cycle. Whereas if you were just using this result on the right, you would need n to the 4/3 edges. So that's kind of the flavor of, yeah, so like basically this result is the reason why the theorem about like this is how you prove that if you don't have any 6 cycles, you have to have a very small number of capped 3 walks, and the same thing for any other value of k. So that's how you would prove that. So what would we want for listing? Well, it turns out that what would be really nice is what's called like a supersaturation analog of this extremal number result. Okay, so kind of this is not a new idea. This is like actually feels like a very common theme in combinatorics. So we have some threshold where like below this threshold you might not have any 6 cycles, but then once you get above it, you start getting a ton of 6 cycles. So like there's a classic result that says just what I just said, which is if you have more than like the critical threshold number of edges, then the number of 6 cycles that you have scales like this number, where the way you should think of this number is it's the number of 6 cycles or C2Ks that you would have in a random graph with that edge density. Okay, so that's nice. This is not going to be strong enough for us because it's only in the balanced case, and we want something that's much stronger and is tailored to this unbalanced case. So the thing that it turns out would just give you a C2K listing algorithm for all values of K is the following conjecture. It's basically just says something like, some kind of unbalanced supersaturation result. It says if you have more than the kind of critical number of edges, then the number of C2Ks that we expect between these two parts is at least as many as we would get in a random graph, is basically what this says. Okay, I mean, so I said it's a conjecture, so we don't actually know how to prove this yet. But it turns out that even without having proved this result, we were still able to get some kind of improvement over the previous state of the art for listing algorithms. And yeah, so I'll tell you about that now. So basically the way that our improvement works is as follows. We have some lemma where we take a graph and we are able to make this really nice layered decomposition of it, where there's some kind of regularity property between the vertex sets, and somehow this layered decomposition facilitates counting the cap walks in a really nice way. And using this layer decomposition, we're able to, first off, we get a really nice, simple analysis of the DKS detection algorithm, which is notably, in my opinion, much simpler than the original analysis. But more than that, I guess another nice consequence is using this layer decomposition, we immediately get that the conjecture, this unbalanced supersaturation conjecture, would imply what we think to be optimal listing for all K. So, I mean, those are both really nice, but I guess maybe for us, the kind of real place where we're using this layer decomposition is we're able to show, using this layer decomposition, that even if we make a little bit of progress towards this unbalanced supersaturation conjecture, we can, in some non-trivial way, convert that into some progress towards a listing algorithm, which is what we did. That's how we got this m to the 1.6 number. So yeah, so I guess maybe one key ingredient of that is we need to have some kind of weaker version of supersaturation to plug in there, and we prove something like that. So we kind of aren't able to fully establish this conjecture, but for C6s we do it in some specific cases. And this is kind of pretty technically challenging, and it's pretty interesting that we weren't able to just actually prove the supersaturation conjecture. So is the supersaturation conjecture even true? I don't know, but I think it could be. So anyways, and then I guess our third result is just combining these things, we're able to get this new listing algorithm. And one kind of interesting thing about how we do that is we're somehow able to turn the problem into like a bunch of linear programs, and then kind of solve these all on a computer. And that's kind of some fun or unfortunate part of our proof for actually getting this listing algorithm out of this. So So yeah, I think that's pretty much what I wanted to tell everyone about. I think maybe the summary of this talk is um, listing is feels like a really fundamental problem, and it feels kind of surprising that we don't know how to do it yet, and then there's so much kind of open questions here. Um, but it feels like there's a lot of like there's a lot of uh, like we it feels like we have some of the ideas, but just maybe don't know how to get them to go through. I guess we saw that if you could prove this unbalanced supersaturation conjecture, then that would just let you do listing. And then maybe you also saw that we don't necessarily need the unbalanced supersaturation conjecture. Maybe you can have some more, some combinatorial algorithm that just goes through some other route. So anyways, I hope you thought it was interesting. And just to finish, I'd like to thank Nathan and Claire for yeah, a lot of really good discussions about some yeah proof attempts for working on this problem. And yeah, thanks.